What we're going to do now is we're going to derive an equation for the work in a steady flow device whereby we're assuming that it is behaving in a reversible manner. And in doing this, what we're going to do is we're going to use Gibbs' equation and the first law applied to a reversible system. So with Gibbs' equation, we saw that when we were deriving the change in entropy in either a solid, a liquid, or an ideal gas, but what we're going to do now is we're going to use Gibbs' equation to derive another expression for work. So we already have a few expressions for work that we've seen thus far in the course. We had one for a closed system, and that was basically the boundary work. So for a closed system, we saw the boundary work was an integral of p dv. And with that, we were able to calculate the amount of work within a closed system if it has a moving boundary. For example, the piston cylinder device is a very common one. Now, for an open system, we can use the first law to come up with a formulation for the work in a steady flow device. So let's take a look at that now. And let's assume that we're dealing with a single stream, steady flow, and we'll also assume that we do not have heat transfer, nor do we have change in kinetic energy or potential energy. So with that, our first law looks like follows. So the potential energy term. Now we said that there is no heat transfer, so the Q term is gone. We said that there is no kinetic energy, so the kinetic energy term is gone. And we said that there is no change in potential energy, so that disappears as well. And what we're left with is an expression. And notice this is a capital W because we have mass flow rate on the right-hand side. And so with the units, that would then be in terms of kilojoules. If we divide both sides by, actually that's kilojoules per second, would be the units there. But if we divide both sides by the mass flow rate, we then get the small w term for work, and that would then be in kilojoules per kilogram. And taking the minus sign over to the right-hand side, we get H1 minus H2. So those are two different forms of equations for work. One for a closed system where we have moving boundary, and then the other for an open system. What we're going to do now is we're going to apply the first law for a reversible system, and we're going to try to come up with an equation that provides us with an estimate of reversible flow work. So again, this is an idealization because no process ever will be reversible, but it's one that we will use as a reference value. So we're going to apply the first law to a steady flow device. And we will also assume that it's undergoing a reversible process. So with that, our first law looks like this. And we denote REV as a subscript for reversible. Okay, so that is the first law to a steady flow device undergoing a reversible process. Now what we're going to do, we're going to pull in our definition of entropy as well as Gibbs equation. So with entropy, we saw when we discussed the Clausius inequality that entropy can be expressed that way. And we also came up with Gibbs equation, so what we're going to do, we're going to take these two relationships and we're going to combine them to provide us with an expression for the reversible heat transfer in terms of enthalpy and specific volume and pressure. And we're now going to take that term here and we're going to substitute it up into there in our first law. So with that, we come out with this expression. We're now going to integrate that and the units here are kilojoules per kilogram. So that provides us with an expression. What we're going to do now is we're going to neglect both the kinetic energy and the potential energy. So those two go away. And what we're left with, so neglecting kinetic energy and potential energy, what we are then left with for reversible work is the following relationship. So this is a relationship for reversible work in a steady flow device, and notice that it is in a way kind of similar to the one that we saw earlier for boundary work of an open system or a closed system. So there are similarities between the two, however they're applied to very, very different systems. On the left, this is for an open reversible, and on the right this is for a closed system. So what we're going to do, let's take a closer look at this. If we're looking at a pump or a compressor, for example, these are devices whereby we are doing work on the system, and consequently by our definition of work, work would be negative, and consequently if we put in negative work, then we can write reversible work in is equal to plus integral from 1 to 2 specific volume dP. So this is an equation that we can now take a look at, and we can look at different types of processes, and what we will specifically look at in the next segment is looking at a compression process. So that is a reversible equation for work for a steady flow device.